Welcome to Chapter 14 of our journey through the fascinating world of statistics. In this chapter, we'll be delving into the critical topic of inference for regression. This chapter is a vital part of our exploration of statistical concepts, as it builds on everything we've learned so far and takes us deeper into understanding how we can make predictions and inferences based on data. Now, you might be wondering, why is inference in regression so important? Well, throughout this course, we've been learning how to describe and summarize data, how to understand the relationships between variables, and how to use that information to make predictions. But making predictions is just the beginning. The real power of statistics lies in our ability to measure the uncertainty of those predictions and to make informed decisions based on that understanding. Inference in regression allows us to take the next step. It enables us to go beyond simply describing the relationship between two variables to making confident statements about the entire population from which our sample data was drawn. In other words, we use inference to generalize our findings from the sample to the broader population, which is the ultimate goal of most statistical analysis. In this chapter, we're going to focus on the linear regression model, a fundamental tool in statistics that helps us understand and predict the behavior of one variable based on another. This model is widely used in various fields, from economics and biology to engineering and social sciences, making it an essential part of your statistical toolkit. We'll start by reviewing the key components of the linear regression model, ensuring that we have a solid understanding of how it works. Then, we'll dive into the process of making inferences using this model, which involves checking certain conditions, understanding residuals, and learning how to measure our uncertainty. As we move forward, you'll see how we can apply these concepts in real-world situations, using examples and visualizations to bring the theory to life. By the end of this chapter, you should feel confident in your ability to not only describe relationships between variables, but also to make sound predictions and inferences that you can rely on. So let's get started on this exciting chapter. We'll begin by exploring section 14.1, which covers the linear regression model in detail. This will set the foundation for everything else we'll discuss, so pay close attention as we unpack the key elements of this powerful statistical tool. Now, as we move into section 14.1, we begin our in-depth exploration of the linear regression model. This section is crucial because it lays the groundwork for everything else we will discuss in this chapter. The linear regression model is one of the most widely used tools in statistics, allowing us to summarize the relationship between two numerical variables and use that relationship to make predictions. However, for the predictions and inferences we make using this model to be valid, we must ensure that certain conditions are met. This section focuses on the critical task of checking that the four conditions of the linear regression model hold. These conditions are not just technicalities, they are fundamental to ensuring that our model accurately reflects the underlying data and that the conclusions we draw are reliable. Throughout this section, we will discuss each of these four conditions in detail. We'll explore why they are important, how to check if they are met, and what steps to take if they are not. Understanding these conditions is essential for anyone looking to apply linear regression in a real-world setting. By the end of this section, you will have a clear understanding of the necessary steps to validate a linear regression model and the confidence to apply these techniques in your own work. Let's dive in and start by discussing the first of these conditions in the upcoming slides. At the heart of our statistical analysis is the concept of a statistical model. So, what exactly is a statistical model? A statistical model is essentially a set of features or assumptions that we believe our data should exhibit. It acts as a simplified representation of reality, allowing us to make sense of the data we collect. Think of it as a framework that helps us interpret patterns, trends, and relationships within our data. The key to a successful statistical analysis lies in how well our model fits the reality it aims to represent. The closer our model aligns with the actual data, the more accurate and reliable our inferences will be when we apply the model to make predictions or draw conclusions. In this context, the purpose of building a statistical model is not just to describe the data we have, but to make meaningful inferences from it. This is where the art and science of statistics come together, balancing the theoretical assumptions of the model with the practical realities of the data. As we continue, we will see how the components of a linear regression model serve this purpose, helping us bridge the gap between our data and the real-world phenomena it represents. The closer our model mirrors reality, the better positioned we are to make valid, reliable inferences from the model to reality. Let's take a moment to review the key concept of the linear regression model, which is central to our discussion in this chapter. The linear regression model is a powerful tool in statistics, and at its core is the regression line. This line serves as a summary of the association between two numerical variables. Essentially, it provides a way to express how one variable, known as the predictor, relates to another variable known as the response. By plotting these variables on a graph, the regression line gives us a visual and mathematical summary of this relationship. In our previous discussions, we focused on ensuring that this association was linear. This means that the relationship between the two variables can be effectively described by a straight line. When the relationship is linear, we can use the regression line to summarize, describe, and even make predictions about the association between the variables. However, up until now, our focus has been on describing the relationship without considering the uncertainty that comes with making predictions or inferences about a larger population based on our sample data. In other words, while we have used the regression line to summarize and predict, we haven't yet discussed how confident we can be in those predictions, or what our level of uncertainty might be. As we move forward, we will begin to address this crucial aspect, understanding and quantifying our uncertainty when making predictions or inferences using the linear regression model. This understanding is what transforms our analysis from simply descriptive to inferential, allowing us to make more informed and reliable decisions based on our data. As we continue our exploration of regression, it's important to recognize that describing the association between variables is only part of the picture. In this chapter, our goal extends beyond merely summarizing relationships. We aim to measure the uncertainty involved in these associations. Understanding and quantifying uncertainty is crucial because it allows us to move from simple descriptions to making robust inferences about a larger population. In other words, we want to be able to take the relationship we observe in our sample and make educated predictions about the population from which our sample was drawn. But in doing so, we must acknowledge that there is always a degree of uncertainty in our predictions. This chapter will guide you through the process of not just creating a statistical model, but one that accurately measures this uncertainty. We'll explore the tools and techniques that statisticians use to quantify how confident we can be in our predictions. By the end of this chapter, you will have the skills to assess and express the level of uncertainty in your regression models, making your analysis more informative and reliable. Let's now move forward to understand how to build these statistical models and incorporate the concept of uncertainty into our inferences. This is where the true power of statistical modeling shines, as we take the step from description to meaningful prediction and decision-making. To build a solid understanding of how the linear regression model works, we need to break it down into its fundamental components. The model we use in regression can be thought of as operating in two main steps, each contributing to how we predict the response variable. One, deterministic component. The first step involves the deterministic component of the model. For any given value of the predictor variable, let's say the number of hours studied, we can use a straight-line equation to calculate the expected value of the response variable, such as the exam score. This straight-line equation represents the ideal relationship between the predictor and response variables, assuming that everything follows the model perfectly. In essence, the deterministic component provides us with a baseline prediction based solely on the observed relationship between the variables. 2. But as we know, real life is rarely this neat and tidy. In reality, there are countless factors that can cause the actual value of the response variable to deviate from our prediction. This brings us to the second step, the random component. This is where random noise comes into play. The random component accounts for the variability in the data that isn't captured by the deterministic component. It's this noise that causes the observed value of the response variable to fall slightly above or below the predicted line. This variability might be due to factors we didn't measure or simply due to random fluctuations in the data. Understanding these two components is critical. The deterministic component gives us our best guess based on the data, while the random component acknowledges that our predictions are not perfect and allows us to measure the uncertainty in those predictions. Together, these components form the backbone of the linear regression model, enabling us to make predictions and inferences while accounting for the inherent randomness in the data. To make these concepts more concrete, let's walk through a practical example involving the lengths and widths of library books. Imagine we have a sample of 24 library books. For each book, we measure both its length and its width. Our goal is to understand how the number of pages in a book might predict its width. To do this, we use a regression analysis, which provides us with the following equation. Text predicted width equals 6.22 plus 0.0366. This equation represents the deterministic component of our model. It gives us a way to predict the width of a book based on the number of pages it has. For example, if a book has 203 pages, we can plug this number into our equation to predict its width. Text predicted width equals 6.2 times 203, 13.6498 text meet. So, according to our model, a book with 203 pages should be about 13.6498 millimeters wide. However, it's important to remember that this is just a prediction based on the deterministic component of our model. In real life, the actual width of the book might differ slightly from this predicted value. This discrepancy occurs because the deterministic model does not capture every factor that might affect a book's width. There is always some random variation, or noise, in the data. On the next slide, we'll look at how well this model's predictions match up with the actual measured widths of 4 specific library books. This comparison will help us understand how much the random component influences our predictions in real-world scenarios. Continuing with our example of the library books, let's examine how the predictions from our regression model compare to the actual measurements. On the left side of the slide, you see a graph that displays the predicted widths of 4 library books based on the number of pages each book has. The line represents the relationship predicted by our regression equation, which we discussed on the previous slide. Now, on the right side, we have a more detailed view. This graph shows both the predicted widths and the actual widths of the same 4 books. The predicted values still follow the red line, but the blue dots represent the actual measurements we took. As you can see, the actual widths of the books do not always match the predictions exactly. In some cases, the actual width is slightly greater than what the model predicted. In other cases, it is less. This variation occurs because, as we discussed earlier, the deterministic component of our model can't account for every factor that influences the width of a book. There's always some random noise or variability in the real world. This visual comparison highlights the importance of understanding and measuring the uncertainty in our predictions. The differences between the predicted and actual values, these are what we refer to as residuals, are a key aspect of evaluating how well our model performs. In the following slides, we'll delve deeper into how these residuals are calculated and what they tell us about the accuracy and reliability of our regression model. Let's now focus on the concept of residuals, which is central to understanding the accuracy and reliability of our regression model. A residual is defined as the difference between the actual or observed value of the response variable, y, and the predicted value of y that lies on the regression line. In simple terms, the residual tells us how far off our prediction was from the actual observed value. Mathematically, we express the residual as text residual equals text actual value, text predicted value. So, if we predict that a book should be 13.65 millimeters wide based on its number of pages, but in reality the book is 14 millimeters wide, the residual would be tex equals 14 minus 13.65 equals 0.35 tex millimeters. This positive residual indicates that our prediction was slightly less than the actual width. On the other hand, if our prediction was greater than the actual value, the residual would be negative, showing that we overestimated the width. The collection of all residuals from a dataset gives us insight into the overall performance of our model. If most residuals are small, it means our model is doing a good job at predicting the response variable. However, if the residuals are large, it suggests that there's a significant amount of random variation or other factors that our model isn't capturing well. The standard deviation of all the residuals, represented by the symbol sigma, is a critical measure in this context. It quantifies the average amount of random variation present in our predictions. In other words, sigma provides a summary of how much the observed values deviate, on average, from the predicted values due to this random noise. Understanding residuals is key to assessing the effectiveness of our regression model, and it's something we'll explore further as we continue to refine our approach to making accurate predictions and reliable inferences from our data. To ensure that our linear regression model provides reliable and accurate results, it's essential that certain conditions are met. These conditions help validate the assumptions underlying the model and ensure that the inferences we draw are sound. There are 4 key conditions that must hold for a valid linear model. 1. Linearity. The first condition is that the relationship between the predictor and response variables must be linear. This means that the trend we observe in the data should follow a straight line. If the relationship is nonlinear, our linear model may not be appropriate, leading to inaccurate predictions and inferences. 2. Normality. The second condition is normality. Specifically, the residuals, the differences between the observed and predicted values, should follow a normal distribution. This distribution should have a mean of 0 and a standard deviation represented by sigma. In statistical terms, the residuals should be normally distributed with mean 0 and standard deviation sigma, denoted as n0 sigma. This condition is crucial for the validity of many inferential statistics we use, such as confidence intervals and hypothesis tests. Number 3. Constant standard deviation. The third condition is that the standard deviation of the residuals should be constant for all values of the predictor variable. In other words, the spread of the residuals should be roughly the same across the entire range of predictor values. This condition is also known as homoscedasticity. If the standard deviation changes, a situation known as heteroscedasticity, it can indicate problems with the model, such as missing variables or an incorrect functional form. 4. Independence. Finally, the residuals should be independent of each other. This means that the error in one observation should not be related to the error in another observation. Independence ensures that our observations are not influencing each other, which is critical for valid statistical inference. For example, knowing that one residual is positive should not give us any information about whether the next residual will be positive or negative. When these 4 conditions, linearity, normality, constant standard deviation, and independence, are satisfied, we can be confident that our linear regression model is appropriate for the data. This, in turn, allows us to make reliable predictions and draw accurate inferences about the relationships between variables. If any of these conditions are violated, it may be necessary to revisit the model and consider alternative approaches. To ensure that our linear regression model is valid, it's essential to check the conditions we just discussed: linearity and constant standard deviation. One of the most effective tools for doing this is a residual plot. A residual plot is a type of scatter plot that can help us visualize how well our model meets these conditions. In a residual plot, the residuals, the differences between observed and predicted values, are plotted on the vertical axis, while the original predictor values, the x values, are plotted on the horizontal axis. This plot allows us to zoom in on potential problems in the model. By examining the pattern of residuals, we can more easily spot deviations from the linearity condition and assess whether the standard deviation is constant across all values of the predictor variable. For example, if the residuals are randomly scattered around the horizontal axis with no clear pattern, This suggests that the linearity and constant standard deviation conditions are likely satisfied. However, if we observe a pattern, such as a curve or a fan shape, this indicates that one or both of these conditions may not hold, signaling a problem with our model. Residual plots are incredibly useful because they make these issues much easier to detect than simply looking at the original scatterplot of the data. As we move forward, we will explore how to interpret these plots and what to do if we find that the conditions are not met. Let's now take a closer look at an example using residual plots to evaluate our linear regression model. On the left side of this slide, you see a scatter plot that shows the cost of a plane trip plotted against the distance traveled for 4 different trips. The red line in this graph represents the regression line, which is our model's prediction of the relationship between distance and cost. The colored vertical lines connecting the data points to the regression line are the residuals. These residuals show how far each actual data point deviates from the predicted value on the line. On the right side of the slide, the residuals are plotted directly against the distance traveled, creating a residual plot. Here, the residuals are represented as individual points, with their distance from the horizontal axis indicating how much the actual cost deviates from the predicted cost. The horizontal axis represents the predictor variable, in this case, the distance traveled. What this residual plot tells us is crucial. We want to see the residuals randomly scattered around the horizontal axis with no discernible pattern. This would suggest that our model is capturing the relationship well and that the linearity and constant standard deviation conditions are satisfied. However, if we observe a pattern in the residual plot, such as a curve, a funnel shape, or clusters of residuals, this could indicate problems with the model. For example, a funnel shape could suggest that the standard deviation of the residuals is not constant, which would violate one of our key conditions for a valid linear model. The good news is that most statistical software packages can automatically generate residual plots for you, making it easier to assess whether your model meets the necessary conditions. By carefully examining these plots, you can diagnose potential issues and take steps to refine your model, ensuring that your predictions and inferences are as accurate and reliable as possible. Now, let's focus on how to check the linearity condition using a residual plot. When the relationship between the predictor and response variables is truly linear, the residual plot should exhibit no clear pattern or slope. In other words, the residuals should be randomly scattered around the horizontal axis, showing no systematic deviation. This indicates that our linear model is appropriate for the data. However, if the relationship is nonlinear, the residual plot will reveal this by displaying some sort of trend or pattern. For instance, you might see the residuals forming a curved shape, indicating that a straight line isn't the best fit for the data. This kind of pattern suggests that the underlying relationship between the variables is more complex than a simple linear trend, and a different type of model might be needed. By closely examining the residual plot, you can determine whether the linearity assumption holds. If it does, you can proceed with confidence that your linear regression model is valid. If not, you'll need to consider alternatives, such as transforming the data or using a more appropriate model that better captures the nonlinear relationship. To further illustrate the concept of checking linearity, let's examine this example involving the number of pages in a book and its width. On the left side of the slide, you see a scatter plot that shows the relationship between the number of pages in a book and its width. The red line is our regression line, representing the predicted relationship based on the linear model. On the right side, we have the corresponding residual plot. This plot shows the residuals, the differences between the actual book widths and the widths predicted by the regression line, plotted against the number of pages. Notice that in the residual plot, the residuals are scattered around the horizontal axis with no clear pattern, slope, or trend. This random scatter of residuals suggests that the linear model is appropriate for this data because the linearity condition is satisfied. The lack of any visible pattern or curvature in the residual plot indicates that the relationship between the number of pages and the width of the book is indeed linear. When the residual plot shows no trend or slope, as it does here, we can be confident that our assumption of linearity is valid and that the linear regression model provides a good fit for the data. Let's now look at an example where the linearity condition is not met to understand how this affects our model. On the left side of the slide, we have a scatter plot showing the relationship between the number of floors in a building and the building's height in feet. The red line represents the linear regression model's prediction of this relationship. On the right side, you see the corresponding residual plot. Unlike the previous example, this residual plot shows a clear pattern, some form of trend or curvature in the residuals. The residuals are not randomly scattered around the horizontal axis, but instead seem to form a pattern that suggests a systematic deviation from the regression line. This pattern in the residual plot indicates that the relationship between the number of floors and the height of the building is not linear. The linear model, therefore, does not adequately capture the complexity of this relationship. This lack of linearity suggests that a different type of model, perhaps a polynomial regression or another nonlinear approach, might be more appropriate for this dataset. When you observe such a pattern in the residual plot, it's a clear signal that the linearity assumption is violated, and the linear regression model may not provide accurate predictions. In these cases, it's important to explore other modeling options that better fit the underlying data structure. When assessing the linearity of data, you might wonder whether simply looking at a scatter plot is enough to determine if the relationship between variables is linear. In many cases, the answer is yes. A scatter plot can give you a good sense of whether the trend appears linear or not. However, scatter plots can sometimes be deceiving. A trend might look linear at first glance, even though it actually isn't. This is where residual plots become incredibly valuable. Think of the residual plot as a sort of microscope that allows you to detect subtle nonlinear patterns that may not be immediately visible in a scatter plot. By examining the residual plot, you can identify whether there are any underlying patterns that suggest the relationship is more complex than it initially appears. This additional layer of analysis ensures that you're not overlooking any nonlinear trends that could impact the validity of your linear model. So, while scatter plots are a useful starting point, residual plots provide a more thorough check for linearity, helping you make more accurate and informed decisions about your model. Let's examine a scenario that highlights why we need to be cautious when determining linearity from a scatter plot alone. On the left side of the slide, you see a scatter plot that shows the depth of lemonade in a container as it is being drained over time. At first glance, the trend in the scatter plot might appear to be linear, suggesting that as time progresses, the depth of lemonade decreases at a consistent rate. However, when we look at the residual plot on the right, we see a different story. The residual plot reveals a strong pattern that indicates a clear deviation from linearity. This pattern suggests that the relationship between time and depth is not linear, even though the scatter plot might have suggested otherwise. In this case, the data actually follows a quadratic curve rather than a straight line. This example underscores the importance of using residual plots as a diagnostic tool. While a scatter plot might seem to show a linear trend, the residual plot can uncover subtle nonlinearities that are not immediately obvious. By using residual plots, you can avoid the mistake of incorrectly assuming a linear relationship when the data suggests otherwise. Let's now discuss the importance of checking the constant standard deviation, SD condition, in a linear regression model. The constant SD condition, also known as homoscedasticity, requires that the standard deviation of the residuals, the differences between observed and predicted values, remains the same across all values of the predictor variable. Essentially, this means that the amount of vertical spread around the regression line should be consistent across the entire range of data. When this condition is met, the variability of the response variable is constant, regardless of the value of the predictor variable. If this condition is violated, it suggests that the model's predictions are more accurate for some values of the predictor variable than others, which can lead to unreliable inferences and predictions. One way to detect whether this condition holds is by examining the residual plot. If the residuals are spread out consistently across the plot, with no discernible pattern, it indicates that the constant SD condition is likely satisfied. However, if the residual plot displays a fan shape, where the spread of the residuals increases or decreases as you move along the horizontal axis, this is a sign that the constant SD condition does not hold. A fan shape indicates that the variability of the residuals changes across the range of the predictor variable, which violates the assumption of homoscedasticity. When you observe a fan shape in the residual plot, it may suggest the need to transform the data or consider a different modeling approach to address the non-constant variance and improve the model's reliability. Let's take a closer look at an example that demonstrates a violation of the constant standard deviation SD condition. On the left side of the slide, we have a scatter plot showing data with a non-constant standard deviation. Notice how the vertical spread of the data points increases as the values of the predictor variable x increase. This indicates that the variability of the response variable is not consistent across all values of the predictor. On the right side, we have the corresponding residual plot. This plot clearly shows a fan shape, which is narrow on the left and widens as the x values increase. This fan shape is a telltale sign that the standard deviation of the residuals is not constant. In other words, the variability of the residuals increases with the value of the predictor variable, indicating that the data does not meet the constant SD condition. When you encounter a fan-shaped residual plot like this, it suggests that the assumption of homoscedasticity, constant standard deviation, is violated. This can lead to inefficient estimates and inaccurate inferences. To address this issue, you might consider transforming the response variable, applying weighted regression, or exploring other modeling techniques that account for the changing variability. Understanding and identifying when this condition is violated is crucial for ensuring that your regression model provides reliable and valid results. Next, let's discuss how to check the normality of the residuals, which is an important assumption in linear regression. To determine whether the errors or residuals follow a normal distribution, we can analyze the distribution of the residuals using two main tools, a histogram or a QQ plot, quantile-quantile plot. Both of these graphical methods help us assess whether the residuals are approximately normally distributed. A histogram provides a visual representation of the distribution of residuals, allowing us to see if they resemble the familiar bell-shaped curve of a normal distribution. However, while histograms are useful, they can sometimes be misleading, especially with smaller sample sizes or when the distribution is close to normal but not quite. A QQ plot, on the other hand, is often more informative. This plot compares the quantiles of the residuals with the expected quantiles of a normal distribution. If the residuals are normally distributed, the points on the QQ plot will fall along a straight line. Deviations from this line indicate departures from normality, making it easier to spot even subtle deviations from the normal distribution. In most cases, a QQ plot is more useful than a histogram for assessing normality because it provides a clearer and more detailed picture of how the residuals compare to the expected normal distribution. Checking normality is crucial for ensuring the validity of various statistical tests and confidence intervals used in the analysis. Let's look at an example to see how we can check the normality of residuals using both a residual plot and a QQ plot. On the left side of the slide, we have a residual plot for a regression line predicting the cost of a home based on its size in square feet for a sample of homes in Long Beach, CA. This plot helps us check for patterns or deviations that might indicate issues with the linearity, constant standard deviation, or other assumptions. However, to specifically check for normality, we focus on the distribution of the residuals. On the right side, we see a QQ plot of the residuals. This plot compares the observed distribution of the residuals to a theoretical normal distribution. Ideally, if the residuals are normally distributed, the points on this QQ plot should fall along a straight diagonal line. However, in this example, the QQ plot shows that the points deviate from a straight line, indicating that the residuals are not normally distributed. The histogram also shows some skewness, further confirming that the normality assumption is violated. When residuals are not normally distributed, it suggests that the underlying assumptions for certain statistical tests may not hold, potentially leading to incorrect inferences. This could mean that the model needs to be adjusted or that a different approach should be considered to account for the non-normality of the residuals. The final condition we need to check for a valid linear regression model is the independence of the observations. Independence means that the residuals' errors should not be correlated with each other. In other words, the error in one observation should not influence or be related to the error in another observation. Unfortunately, checking the independence condition is not something that can be easily done by simply looking at the data or using a residual plot. Independence is more about how the data were collected and the underlying structure of the data itself. For example, if the data were collected sequentially over time, there might be a risk of autocorrelation where consecutive observations are related. In most practical situations, you will have to assume that the independence condition holds based on how the data were gathered and the design of your study. However, it's important to be aware that if this assumption does not hold, it can significantly affect the validity of your conclusions. If it is later discovered that the data are not independent, the inferences and predictions made using the model might not be reliable. Therefore, while we often proceed with the assumption of independence, it's crucial to consider the data collection process and potential sources of correlation when evaluating your model's results. If independence is in doubt, further investigation or alternative methods, such as time series analysis or mixed models, may be required. To wrap up our discussion, let's summarize the key steps for checking the conditions required for a valid linear regression model. 1. Linearity. Use a residual plot to check for linearity. If the residual plot shows no trend or pattern, the linearity condition is satisfied. The residuals should be randomly scattered around the horizontal axis, indicating that the linear model is appropriate for the data. 2. Constant standard deviation. Again, use a residual plot to check for constant standard deviation, homoscedasticity. If the residual plot displays a fan shape, where the spread of residuals increases or decreases as the values of the predictor variable change, this indicates that the constant SD condition is not satisfied. A consistent spread of residuals across the plot suggests that this condition is met. 3. Normality. To check for normality, make a QQ plot of the residuals. If the points on the QQ plot mostly follow a straight line, this suggests that the residuals are normally distributed, satisfying the normality condition. Deviations from the straight line indicate that the residuals may not be normally distributed, which could affect the validity of the regression model. 4. Independence. Finally, review any information you have about how the data were collected to assess whether the independence condition is satisfied. Since independence cannot be directly checked through plots or visualizations, it's important to consider the study design and data collection process. If the data points are independent, the condition is likely satisfied. If there is reason to believe the data points might be correlated, e.g., time series data, further analysis or different modeling techniques may be needed. By systematically checking these conditions, you can ensure that your linear regression model is appropriate for your data, leading to more reliable and valid conclusions.